Look into the pale Delhi sky and the aircraft almost disappear. 75 drones are moving above an Army Day parade ground. Scouts search. Other machines attack mock radar sites and armored targets. Then comes the detail that turned a formation into a system. A six-rotor carrier described by outside analysts as a mothership, releasing smaller quadcopters to continue the mission. Online, this aircraft is now often called the BEL VAHAK-6. The footage is real. The public name is not. No official Bharat Electronics page, Indian Army release, or manufacturer document reviewed for this film identifies a platform by that designation. So this is not a brochure retold. It is an investigation into what the 2021 demonstration actually showed, who built the operational system that followed, how an airborne drone carrier could work, and where spectacle ends and verified capability begins. Start with the name. Vahak means carrier in several Indian languages, which makes it a persuasive label for drone carrying drones, but a plausible name is not evidence. Bharat Electronics publicly says it has displayed a hexacopter, a tethered UAV, and a swarm of UAVs. Its annual reports list swarm systems among technology and business areas. That proves BEL has relevant work. Does not connect BEL to the six-rotor mothership seen at the 2021 parade, and it does not establish a product called VAHAK-6. The Army's official release did not name the startup involved. Contemporary reporting did. NewSpace Research and Technologies. NewSpace now publishes Beluga and Nimbus as members of a heterogeneous UAV family. The disciplined conclusion is therefore narrow. BEL and NewSpace both work on unmanned systems, but the famous parade swarm and the later Army procurement are publicly associated with NewSpace, not with a verified BEL VAHAK-6. Fixed point is January 15, 2021, at Delhi Cantonment. The Press Information Bureau recorded a live Army Day demonstration using 75 indigenously designed and developed drones. It described artificial intelligence-enabled simulated offensive missions and close support tasks, and called the project the beginning of the Army's engagement with autonomy and weapon platforms. Surviving recordings show dots forming across the sky, target boxes from airborne cameras, smoke and controlled detonations on the parade ground, then logistics and medical support sequences. These are authentic views of the public event, although the copies used here come from news and defense channels and are shown only as attributed excerpts. The demonstration matters because it linked several roles in one performance, but it was a prepared event over a known range. It cannot by itself prove battlefield resilience, independent target recognition, resistance to electronic attack, or the ability to repeat the mission beyond a scripted geometry. The most important word is heterogeneous. A homogeneous swarm repeats one airframe many times. A heterogeneous swarm divides labor among machines with different sizes, sensors, and payloads. Analysts studying the parade footage identified three apparent classes: a quadcopter for sensing, a larger six-rotor mothership, and small explosive-laden quadcopters. Government Police Research Journal later described the same broad sequence. Scouts found targets, motherships released expendable units, and attack drones completed mock strikes. That structure resembles a team more than a flock. A scout can climb for line of sight. A carrier can spend its battery lifting payload. A small child drone can trade endurance for a short terminal dash. Other members can relay communications or deliver supplies. The gain is specialization. The cost is orchestration. Different speeds, ranges, battery states, and failure modes must be reconciled continuously. Once roles diverge, the swarm's intelligence is not just collision avoidance. It becomes task allocation under changing conditions. I build the carrier around 6 rotors. A hexacopter is not automatically a mothership, but the layout suits the job. More lifting discs can support a heavier frame, sensor package, radio, and release rack. 6 propulsion units also give designers options for control authority, and depending on configuration and software, limited tolerance of a motor failure. Yet every extra arm, motor, and electronic speed controller adds mass and drag. Hovering is energetically expensive because the aircraft must accelerate air downward for every second it stays aloft. The carrier therefore lives inside a brutal budget. Batteries, structure, and avionics consume mass before any child drone is attached. Add more children and endurance falls. Add a larger battery, and the motors must lift that battery too. This is why the mothership idea is less about making one giant drone and more about transporting several short-range effects through the inefficient first part of their journey. It is an airborne staging point. Release looks simple only from far away. Beneath a multirotor, propellers drive a turbulent column of air toward the ground. A child drone dropped into that flow can tumble, strike the rack, collide with another vehicle, or be pulled back toward the carrier. A credible sequence needs separation logic. The mothership stabilizes and checks attitude. One latch opens, not all of them. Child falls or is pushed beyond the worst wake, confirms clear distance, starts or increases rotor speed, establishes its own navigation state, then joins the network. The carrier must update its balance after every release because the center of mass changes. The children need unique identities and mission data before separation, plus a safe response if communications never return. Public video does not reveal the latch design or flight control law used in Delhi. The mechanism shown in this film is therefore illustrative, but the physics explains why a successful airborne deployment is itself a meaningful engineering achievement. Numbers alone do not create a swarm. 50 aircraft can be 50 remote control links flying nearby. A true swarm has coordination rules that let the group behave as a system. At minimum, each vehicle needs to know enough about neighbors, space, and mission state to avoid collisions and preserve formation. More advanced behavior distributes tasks. One vehicle finds a target, another confirms it, a relay changes position, and available attackers are assigned without an operator steering every airframe. The official release said the 75 drones performed artificial intelligence-enabled missions. Commentary around the event used words such as autonomous and distributed intelligence. Those statements support an autonomy claim, but the public material does not expose software architecture, test logs, or operator workload. NewSpace now advertises heterogeneous parallel tasks, dynamic retasking, self-healing swarms, and intelligent mesh networks. Those are the right architectural ideas. Their performance under combat pressure remains a question for controlled trials, not a conclusion available from parade footage. Every swarm includes an invisible aircraft. The network, position, tracks, video, task assignments, and health data must move through radio links with limited bandwidth. A direct connection from every drone to one ground station is easy to understand but hard to scale and easy to overload. A mesh lets vehicles relay messages through one another. That can extend reach behind terrain, provide alternate routes when a node disappears, and reduce dependence on a single long link. It also creates difficult choices. Video consumes far more bandwidth than coordinates. Frequent updates improve awareness but reveal emissions and drain power. Encryption and anti-gem waveforms protect the network but demand processing and disciplined key management. Bharat Electronics publicly markets UAV data links with payload and telemetry channels, electro-optical video, communications security, anti-gem features, line of sight, and satellite option. Those capabilities explain where BEL could contribute to a swarm ecosystem. They still do not establish ownership of the Delhi Mothership airframe. Autonomy is not one switch, it is a stack. At the bottom, each drone stabilizes itself. Above that, it navigates a route and avoids obstacles. A coordination layer maintains separation and shares local state. A mission layer allocates roles and replans when a vehicle fails. At the top sits authority, which actions require a human decision, particularly when weapons are involved. Marketing often compresses all 5 layers into the word AI. Engineering cannot. Formation can fly autonomously, while target selection remains scripted. A vehicle can recognize a shape, while a human still authorizes an attack. A group can self-heal its communications without changing its mission. The Army release confirms A-enabled simulated offensive missions, while DRDO lists AI-based swarms for autonomous weapon deployment and kill assessment as a technology development task. Neither source publishes the rules of engagement used in the parade. The responsible reading is that autonomy was demonstrated in some functions, while the depth and limits of that autonomy remain undisclosed. The cleanest demonstration sky is filled with reliable coordinates. A contested sky may lie. Satellite navigation signals can be jammed so receivers hear nothing, or spoofed so a confident position is wrong. Command links can be drowned in noise, detected by direction finding, or attacked through protocol weaknesses. Cameras face haze, smoke, glare, and deliberate camouflage. Swarm survives by degrading gracefully. Inertial navigation bridges short gaps, vision or terrain correlation checks position, the mesh changes routes, and local rules preserve safe flight when the ground station disappears. NewSpace has publicly discussed experiments involving GNSS-denied operations and resilient mesh networking, but public posts are not qualification data. The Mothership introduces another risk. It concentrates child drones, energy, and communications in one visible node. Destroy or disable it before release, and several effects disappear at once. The carrier extends reach, but it also creates a high-value point of failure. Good tactics must release value before the carrier becomes a target. Swarm brochure can list range, endurance, and payload as if all 3 arrive together. They do not. Multirotor endurance falls sharply as mass rises, because greater thrust demands greater electrical power. A carrier loaded with child drones may fly much less far than the same airframe carrying only a camera. Wind, altitude, and temperature alter the budget again. Temporary reporting around the parade said the full group could carry a combined 600 kilograms of supplies, while later public descriptions of the Army's acquired system place individual aircraft in a 5 to 30 kilogram maximum takeoff weight class. These statements describe different levels of the system and should not be merged into one aircraft specification. The useful question is mission payload at mission radius with reserve energy, not the largest number appearing in an article. For a mothership, the payload may be reconnaissance sensors, radio relays, medical supplies, explosive charges, or child vehicles. Every choice produces a different aircraft in practical terms. NewSpace publishes a 50-kilometer radius and a 20,000-foot service ceiling for its heterogeneous system. Jane's reported up to 3 hours of endurance and a 5 to 30 kilogram weight class. Those figures are meaningful because they come from the manufacturer and named reporting about the delivered system. They still require context. Radius may describe communications reach, mission planning, or a particular airframe with a particular load. Service ceiling is not the same as useful hover performance while carrying children. Endurance can refer to a long-endurance Beluga configuration rather than every Nimbus in the group. The 3-hour figure and the 50-kilometer radius should therefore be presented as published system claims, not as independently verified performance of the unnamed 2021 Mothership. This distinction is central to the entire investigation. The parade video, the later Beluga and Nimbus product family, and the internet label VAHAK-6 may describe related ideas. Public evidence does not prove they are one unchanged vehicle. Strongest evidence of maturity arrived 2 years after the parade. Janes reported that NewSpace won an Indian Army contract in September 2021 and completed delivery by March 2, 2023. The contract covered 100 unmanned aircraft and was valued at roughly $15 million. The Army name was Autonomous Surveillance and Armed Drone Swarm, or ASADS. The company identified the aircraft as Beluga and Nimbus models and described roles including kinetic attack, intelligence, surveillance and reconnaissance, and communications relay. Shepard reported the same basic pairing. Beluga hexacopters and Nimbus Mark III quadcopters. A government Make in India project listing separately described an autonomous surveillance and armed drone swarm for desert and plains, with day-night cameras and attack payloads. Procurement is not proof of invulnerability, but it changes the status from a one-day spectacle to fielded equipment. What was purchased publicly carries the NewSpace identity. The VAHAK-6 name remains outside that evidence chain. Bharat Electronics should not disappear from the story simply because the viral name is unsupported. BEL is a major Indian defense electronics integrator. Its official material documents tethered hexacopters for persistent surveillance, development of a hexacopter 20, UAV data links, anti-drone systems, and displays of swarm UAV capability. Its annual report places swarm UAVs among unmanned technologies it is pursuing. These are exactly the kinds of sensors, radios, command systems, and production capabilities a national swarm ecosystem needs. But ecosystems are not single products. A radar company can support a drone without designing its airframe. A data link supplier can connect a swarm without owning the autonomy software. A public exhibition can display a concept without proving it was used in a previous Army demonstration. The honest connection is therefore capability adjacency, not attribution. Until BEL, the Army, or a traceable technical document publishes the VAHAK-6 designation, it should be treated as an unverified internet label rather than a confirmed BEL program. The engineering question eventually becomes a human one. When a swarm detects, classifies, and approaches a target who decides that the target is valid, public descriptions of the Army Day event use autonomy and artificial intelligence, but the targets were simulated and the detailed command chain is not disclosed. There are many possible arrangements. A human may approve every strike. An operator may approve a target set while machines assign individual vehicles. System may act automatically within a bounded defensive zone. Each arrangement changes speed, workload, accountability, and risk. Machine perception can fail through poor imagery, unexpected context, or deliberate deception. Communications can delay an approval at the worst moment. Yet forcing one operator to micromanage dozens of drones destroys the advantage of scale. The hard design problem is meaningful human control at mission tempo, interfaces that show confidence, alternatives, uncertainty, and abort options without turning the operator into a rubber stamp. The parade proved coordination. It did not reveal this governance architecture. A swarm is designed to complicate defense, not to abolish it. Small drones can approach from different directions and force radars, jammers, and guns to divide attention. Cheap attackers may exhaust expensive interceptors. Heterogeneous roles let scouts and relays support vehicles carrying payloads. The defender can answer with layers: detection by radar, radio frequency sensors and electro-optics, broad or directional jamming, navigation deception, high-rate guns, other drones, and command decisions that prioritize the mothership or relay nodes. BEL itself markets the D4 anti-drone system, a reminder that the same industrial base works both sides of the contest. Carrier creates range and surprise before release, but a recognizable larger airframe may also be easier to detect than its children. A mesh can root around losses, yet the swarm still depends on energy, spectrum, and mission logic. The real measure is not whether every drone survives. It is whether enough useful functions survive long enough to complete the objective at acceptable cost. Return to the recording and separate observation from inference. The video proves that a large coordinated set of indigenous drones flew during a public Army event. It shows airborne sensor views, multiple target effects, and support tasks. Official reporting fixes the number at 75 and describes A-enabled simulated missions. Contemporary analysis identifies a six-rotor mothership and small child quadcopters, although the long camera distance makes exact hardware difficult to inspect. Later reporting proves that the Army bought a 100-aircraft NewSpace Heterogeneous swarm using Beluga and Nimbus models. Video does not prove a 50-kilometer combat radius, 3-hour endurance under mothership load, autonomous lethal target selection, performance in severe jamming, or direct BEL product identity. This does not make the demonstration fake. It makes it a demonstration, evidence of integration at a specific place and time. Its value increases, not decreases, when claims are kept inside the boundary of what viewers can actually see and sources can actually support. The next proof will be less theatrical. It will come from repeatable field trials in heat, dust, mountains, and forests, from missions without clean satellite navigation, from measured operator workload, from encrypted networks under interference, and from production batches that behave alike. NewSpace has described foliage penetration, GNSS-denied operations, dynamic retasking, and self-healing mesh networks. The Army and Drone Federation of India have formalized work on testing, manufacturing, and operational requirements. Those directions match the problems exposed by the mothership concept. Airborne release must work repeatedly. Communications must degrade without collapse. Humans must retain appropriate authority. Logistics must support batteries, spares, payloads, and software across a fleet, not a stage. Success may not look like a single giant formation. It may look like smaller teams appearing where needed, sharing information and reassembling around the surviving nodes. The carrier is only one part of that wider combat architecture. So what is the BEL VAHAK-6? On the public record available in August 2026, it is not a verified product designation. It is most likely a convenient name attached to real images of India's six-rotor drone mothership idea, then blended with BEL's genuine work on hexacopters, data links, and swarm systems. The machine in the story is real enough to matter. In 2021, the Indian Army flew 75 drones through a coordinated live demonstration. By 2023, NewSpace had delivered a 100-aircraft heterogeneous system built around Beluga and Nimbus families. The engineering idea is powerful. Move sensors, relays, or small effects inside a carrier's range, release them near the task, and let a distributed team adapt. Its weaknesses are equally real. Mass, energy, turbulent separation, radio dependence, electronic warfare, concentrated vulnerability, and human authority. The mystery is not whether India is building swarms. It is why an unsupported name became more memorable than the documented program. Evidence is the difference between fascination and understanding.